Greetings to all my dear students. Welcome back. In the first video under design of experiments, we had spoken about what an experiment is, what do we mean by designing it, what are the various variables involved in it, and then we spoke about the main objective of DOE, which is the short form of design of experiments. And further, we spoke about the principles involved in design of experiments. So using the principles, we shall discuss three basic designs. So we shall discuss the first design called completely randomized design, or CRD in short, in this particular video. So at first, we shall decide on what this particular design is, what are the merits and demerits of this design, and thereby learn the ANOVA technique, which is the analysis of variance technique, using the F test to find out a solution for these particular design. So these are explained using examples. So three examples have been done elaborately after we start with the basic introduction. So let's begin. So let's begin by discussing the features of the completely randomized design. This design is used when the experimental units are homogeneous, which are meaning similar, and treatments that we are interested in, which is our input data, they are given to these experimental units in absolutely a random fashion. We are interested only in one factor or one treatment, and that is why the CRD is also called a one-way classification. So treatments are given and to the experimental units, and the yield is the output. So this is the only factor which we are interested in. So we would be testing whether there is any significant difference between these treatments. So that's the basic goal of CRD. So the remaining factors which are applicable on the system are ignored in this particular design. That's why we call it to be one-way classification. What are the merits of CRD? It's a very simple layout. It's completely flexible, as replication count is not fixed. So we are not counting on or equating or equalizing all the treatments to have the same number of replications. So we can have one treatment having more number of replications, another one less, and so on. It's a simple analysis, and it can be done even if some observations are missing. And what are the demerits of CRD? The experimental error is large because it's very flexible. We do not have a proper methodology of the replication. Homogeneity of units is not considered. So though we are saying it is homogeneous, it's not mainly considered, and it is less informative. So this is a very ideal case or a very basic kind of a design which is used or which is being taught to understand the structure of how a designing can be done and how ANOVA technique is used to solve that particular design. So we shall now go ahead with the working rule. So let's now begin with the treatments that are defined in the problem. We have K treatments in an experiment, and let me assume that an ith treatment is replicated or repeated Ri times, meaning the first treatment is repeated R1 times, kth treatment is repeated Rk times, and the total yield for each treatment, suppose it's the ith treatment I'm looking at, what is the total yield of the ith treatment? I'm assuming it to be Ti, so that the total number of experimental units will be obtained by adding all the Ri's, where the counter I would run from 1 to k. That is R1 plus R2 plus R3 plus etc. Rk would give you the total number of experimental units. So this is the basic structure given to us in any problem. So the treatments would be given, the final yield would be given, and we would be asked to check whether there is any effect of the treatments on the yield. So we will have to start the procedure by first defining two statements. They are called null hypothesis and alternative hypothesis. The null hypothesis is denoted by the symbol H naught, which is always a statement of no significant difference. So this word no plays a very important role here. We define null hypothesis as a statement which would state that there is no significant difference between the treatments which are under consideration. So we are considering these treatments, say K treatments, and we are checking whether there is any difference in the yield with respect to the treatment. So we are saying in H naught that there is no significant difference. So the negation of H naught is what we call alternative hypothesis, denoted by H1. So this would state that there is significant difference between the treatments which are under consideration. So these are the two statements which we shall define first. One of these is accepted and the other is rejected at the end of the problem. So this could be acceptance of H naught or acceptance of H1. That is what the problem decides. The basic ANOVA technique tells us that. So there is certainly an amount of error that we definitely expect. It's not 100% result that we get. So we define the level of significance for any given problem. It could be 5% in general, it is. It could also be 1% or 2%, meaning if it is 5%, that means the result that we are stating is 95% accurate. If it is 1%, we say it's 99%. If it's 2%, 98%, and so on. Here by default we have chosen it to be 5%. So in any given problem, the first step involves the definition of the null hypothesis, the alternate hypothesis based on the question given to us, and decision of level of significance. So this is given to us. So this is what we decide in step 1. Step 2, what we do is rearrange the given data according to the treatments that are given to us. So we are given a certain number of treatments. Here, of course, it's K. In the example, I have shown only 3. Then what is the yield? That means this treatment is given to certain number of plots. Maybe, but it is not, replications are not the same. We have understood that. So A, maybe treatment is A is given to 4 plots. So I may get 4 values of yield here. The total yield corresponding to treatment A will be added and put here in this position. This is TI. TI is meaning the total yield pertaining to treatment A. Then I'm squaring the TI. Ri represents the number of replications made for the given treatment. If it is 3 or 4, I write that number here. Then I divide Ti square by Ri to get a number here. So this is how I fill up the table. Similarly, corresponding to B, the yield pertaining to the plots it is assigned to. The total number of total yield is Ti. Square of Ti is Ti square. The number of plots given the treatment BI is Ri. I divide Ti square by Ri. So I do that for every treatment and complete this table. Now let us look at the totals. Ti is representing the total yield pertaining to treatment A, that's written here, treatment B, that's written here, treatment C, that's written here. As I have taken only 3 treatments in this example, if I add all the TI, I would get the total yield, or I call it to be the grand total or the grand yield, which I represented by the letter G throughout my designs here. So sigma Ti will give you a total yield that all the treatments together give us, and that we call as G. And when I add up Ri, I get total number of experimental units, which I represent N. As we have seen here, sigma Ri is giving you N. So I add up all these Ri's and I get the total number of experimental units. And the last column gives me the summation of Ti square by Ri, which is the mean value of the treatments. And that I get that here. I use that in my sum of square calculations in my next step. So this is giving me sigma Ti square by Ri. This is giving me the value of N and this is giving me the value of G. Let's remember them so that we can understand the calculation of sum of squares, which we would do in step 3. Now, having defined the hypothesis, decided the level of significance, and also rearranged the data in the required format, now comes the step of calculation of various sum of squares, which we require in the ANOVA table. So there we require total sum of squares, and between sum of squares and an error. The total sum of squares means, which we represented as SST, is given by double sigma Yij square minus G square by N. I am sure you all recognize G is the grand yield, that is the total yield. N is the total number of experimental units. Yij, what is Yij? Yij represents the yield per treatment. So for treatment A, I said you could be given 2, 4, 5. If you are applying it for three respective plots, for B you may get another 1, 4, 7. And for C you may apply it only for two plots. So you may get this as a 6 and 3. So this could be your total. And what does sigma Yij mean? Is the sum of all these. But if I say Yij square, that means I'm squaring each of these yields and I'm adding them. So I square all the yields that I have irrespective of the treatment I'm given, and I add all these up, and that gives me double sigma Yij square. So that gives me a direct result. G and N is obtained from the table which I told you in step 2, and this total gives me this total sum of squares. Coming to between sum of squares, we are checking between the treatments. So I told you there is a mean treatment, mean value for the treatments, the last column in the total. In the previous case that I showed in the previous slide, this is giving me the sigma Ti square by Ri. So that value is taken here, and values of G and N are substituted to get the value of SSB, read as between sum of squares of the treatments. And finally, the error component, which is represented by SSE. So it is a total sum of squares minus between sum of squares. That gives me the value of SSE. These are the three important sum of squares required to construct the ANOVA table, which we shall see in the next slide. So quickly recall what is SST, what is SSB, and what is SSE. So time now to frame the ANOVA table. Look at the columns of ANOVA table. The first one is source of variation. Where can we find the variation? We can find between the treatments or between samples. Now, that's the only classification that we are doing. So that's the only place we can find. And we have an error component. And we compare our table along with the totals that we shall be writing. The second is degrees of freedom. Degrees of freedom are those number of observations wherein we remove the constraints or restrictions are allotted on the observations. So these are also explicitly given to us, and based on which we calculate what is called the table value. So degrees of freedom play a very, very vital role. Sum of squares are the ones which we just now calculated. Between the samples, we called it SSB. Error, we called it SSE. And when you add these two, you need to check whether you get the total SST. And finally, we calculate mean squares, using which we calculate what is called the F ratio or the variance ratio, which decides whether there is variation among the treatments or not. So we calculate the mean square between the samples as the value R1 divided by the corresponding degrees of freedom, which is K minus 1. MSE meaning the error in mean squares of the error is defined as R2. R2 is just SSE, it's only a notation given, divided by N minus K. So we have got the two corresponding values. And now what we do is decide the F ratio. F ratio is the ratio of MSB and MSE. Note that the F value, the F distribution, in the F distribution, the F value is always greater than 1. So it has to be greater than 1. So we should choose the greater value out of MSB and MSE and put it in the numerator. So assuming that MSB is greater than MSE, so we write that as MSB by MSE. If you have MSE to be greater, then you will write MSE in the numerator and MSB in the denominator. And this is the F ratio that you would get by dividing one by the other, and this is called the calculated value of F. Now we shall compare this calculated value with what is called the table value of f. So there is a standard table defining the f ratio based on the degrees of freedom given to us. So once we get the f table, we shall apply that and find out what is the f value pertaining to these degrees of freedom. How did we write the degrees of freedom? If MSB is written in the numerator, corresponding degrees of freedom is k minus 1, and the second component would be MSE, which is corresponding to MSE, it's n minus k degrees of freedom. So it will be F distribution with the components as k minus 1 in the numerator and n minus k in the denominator. I will show you how we see from the F table and get the table value of F based on this degrees of freedom in my next slide. So what we have here is the calculated value, and we now know the degrees of freedom which we have to check for the table value from the given table. Then how do we judge the conclude the answer? I will explain it to you in step 5. So suppose I say MSE is greater than MSB. As I said, the numerator will be MSE, denominator will be MSB. Correspondingly, the order of writing this will also change. So if I have it to be MSE is greater than MSB, then I will write F to be equal to MSE by MSB. And what does it follow? This follows the F distribution. Corresponding to MSE, degrees of freedom is n minus k, and then k minus 1 degrees of freedom. You may wonder why the order matters. Yes, the order surely matters. I shall show you in the table in the next slide. So kindly revise it. We have source of variation having between samples, error and total, degrees of freedom, which is k minus 1 and n minus k, sum of squares, what we found in the previous slide, we call them R1, R2, and SST is the total of these two. Mean squares is obtained by dividing R1 by k minus 1, R2 by n minus k, and the F ratio is obtained by dividing the greater value by this smaller value and deciding how to calculate the table value of f based on the order of degrees of freedom. So this is the gist of ANOVA table, and then let me show you the table and then the conclusions that we make accordingly. So before we come to the conclusion, let me explain to you the F table that I was talking about in the previous slide. And this is an F table of critical values where we have alpha, which is denoted for a notation for level of significance. When I say 5%, it is 0.05. For F, which you see here, DF1 is the first component and DF2 is the second component. The DF1 is the degrees of freedom for the numerator. DF2 is the degrees of freedom for the denominator. So kindly note the numerator is represented along the row and denominator is represented along the column. So if I want to find out the FF table value at 0.05 level of significance for the values 2 comma say 6. So since the first component is 2, I will look through the row wise first where 2 is, then I come down to 6 and then see where is 6. So 2 and 6, so I have that 5.14 to be my table value. So that's how I evaluate the table value in to decide what is the F table value pertaining to the required or the given degrees of freedom. Now that you get the table value from this kind of a table, now we have also the calculated value from our ANOVA table. What we do now is compare the two. Compare the calculated value with the table value that we get for the given degrees of freedom at 5% level of significance. Now, the conclusion that we have would be if the calculated value is less than the table value, then we accept H naught. That is the null hypothesis, meaning that if the calculated value that we get from the ANOVA table is less in value when compared to the table value that we get from this table, then we accept H naught or the null hypothesis. That means there is no significant difference between the treatments which are under consideration. That would be our conclusion. Whereas if the calculated value of F is greater than the table value, we will reject the null hypothesis, meaning we will accept the alternative hypothesis. So in this case, we shall conclude that there is a significant difference between the treatments which are under consideration. So this is the procedure. It's a 5-step process that we go through to evaluate or recognize whether there is a difference or there is no difference between the treatments in the one-way classification category. So step 1, as I repeat, step 1 would be to derive, define the null hypothesis, alternate hypothesis, and level of significance. Step 2, we rearrange the data and derive certain parameters like G, N. So in step 2, we calculate G, N, sigma Ti square by Ri. We make use of this in step 3 and calculate the sum of squares, sum of squares, and the error of sum of squares. So we use these three in the ANOVA table to calculate what is the F calculated value. And then from this table, we calculate the table value and we compare them. So if F calculated value is less than the table value, then we shall accept H naught. If it is not less than, that is, it's greater than, then we will accept the alternative hypothesis and make our respective conclusions. We shall now follow these 5 steps in three given examples from my next slide. I will start from the first one. I have evaluated all the three for the benefit of the students. I hope you will find it simple. We will follow these steps meticulously. Let's read problem 1. A completely randomized design experiment had with 10 plots and 3 treatments gave the following results. Analyze the results for treatment effects. So we are given 10 plots, so 10 experimental units, 3 treatments, and we are given the yield in every plot. So look at the table. Plot number runs from 1 to 10. Treatments are various treatments are given, A, B, and C. There are 3 treatments given, and the yield in corresponding plots are given to us. So we see there is, though here it is completely randomized design is mentioned in the problem, it is easy for us to recognize this problem as a CRD because there is only one factor, which is the treatment affecting the yield. So this is a one-way classification, and therefore we shall proceed as CRD. So let's proceed with the 5 steps as defined earlier. In the first step, we define what is the null hypothesis, alternate hypothesis. Since we are analyzing the results for treatment effects, there is no significant difference between the effect of treatments, and there is significant difference between the effect of treatments is H1. The level of significance we take is 5%. The second step involves the rearrangement of the data. As I told you, if you remember, since it's in the next slide, I will give you a small briefing here itself. We have treatment here and we have yield here. So when I say A is the treatment, I find it fixed here. At what all points I have A here, I have A here, and I have A here and here. So A is applied in 4 plots. So what is the corresponding yield? I will write it as 5, 7, 3, 1. When you look at B, B here is 1 here, 1, and then another B here, another B here. So look at the yields that you're getting. It's 4. Again, you have a 4 and then you have a 7. I will write 4, 4, 7. Similarly, I'll put C. So this is how I fill up the table in step 2. Let's see in my next slide. So as I explained just now, we have taken treatment, yield. This is the table I had given you earlier in the working rule also. Ti square, Ti squared by Ri, which is the main treatments. So for A, I have it applied in 4 plots, which the yield is this. The total yield 5 plus 7 plus 3 plus 1 is 16. Square of it is 256. There are four treatments, 1, 2, 3, 4, 5, 4 sorry, yields pertaining to the treatment A. So I have 4 written here. That is the replications. And Ti square by Ri, 256 by 4 is 64. Similarly, I do for treatment B and C. And as I told you, there are three totals which are important for us: the grand yield or the grand total, which is G, so that's 40. N, which is the total number of experimental units, as he has given it is 10. It coincides here too. And this is sigma Ti square by Ri, which is used to find the sum of squares between the treatments. So we shall use the three values in our sum of square computation in the next step. So here K is 3, N is 10. Now G, which we have noted here, is 40. So what is the total sum of squares? By the formula, it is double sigma Yij square minus G square by N. Each of these is Yij. 7, 5, 5, 7, 3, 1, 4, 4, 7, 3, 5, 1. Each of these is a Yij. So since I need to square and I have a summation, so I square all these terms and then I add them. So it is 5 square plus etc. The last one being 1 square. The total is 200. And G square by N. G square is by N is called the correction factor. Now this is called the correction factor, which we apply to find the sum of the squares between the treatments, or the total sum of squares, or the error. So G square by N that we take is 160. Subtract and therefore get SST to be equal to 40. We calculate between sum of squares in the next slide. So between sum of squares by the formula is mean value of the treatments minus the correction factor. I've got this value from the previous table. I've got this by from the same, and I get the result to be 6. And the error, which is SSE, is the total sum of squares minus between sum of squares. So I'm just subtracting the values which I have found to get 34. I substitute these sum of squares in step 4 in ANOVA table. So as I explained to you earlier, source of variation is between treatments, error and total. Degrees of freedom is K minus 1. Here our K, number of treatments, is 3. Then for error, I have N minus K. Capital N is 10 and K is 3. So it is 7. Total is N minus 1. So 10 minus 1 is 9. 7 plus 2 is 9. It coincides. R1 is SSB, which I have just now calculated, is 6. I am carrying forward here. R2 is SSE, which is 34. So when I add these two, I should get SST. Yes, SST in my previous slide is shown to be 40. Then mean sum of squares between the treatments. What is the mean squares? It is 6 divided by 2, as it's 3. The mean sum of squares of the error is 34 divided by 7. It's 4 point around 86. Now, which is greater out of the two? We see this is greater, MSC is greater. So my F value, as I told you in the working rule, I write the greater value in the numerator, the lesser value of the two in the denominator, because the F value should always be greater than 1. I get it around 1.62. Now, looking at the table value, as I said, if you see 7, take 7 along the row. So you see here it's 7. Now you go along the column, and this point, this value is what you have as 19.35. You may check it from the table. I have found the F table value. Now what is the degrees of freedom that we have considered? Why is it 7, 2 and not 2, 7? Because 4.857 is in the numerator. Corresponding degrees of freedom is 7. So we write 7 as the first component. The denominator is 3. Corresponding degrees of freedom is 2. So the denominator is seen along the column. The numerator is seen along the row. So you see the numerator first, then go down the denominator, and then define the F table value. We find that the calculated value is less than the table value. So by our analysis, The null hypothesis is accepted, meaning there is no significant difference between the effect of treatments. So there is no change in the yield even if we change the treatments. This is the kind of conclusion we make using ANOVA table for a very simple CRD problem. Let's take the second problem in my next slide. Let me now read the second problem for you. The following table shows the lives in hours of four brands of electric lamps. So we are talking about, in the previous problem, we just said treatment and yield. So it was an agricultural research problem. Whereas here we are talking about four brands. So these are the treatments of electric lamps, and we are talking about the mean lives that he wants us to check on. Perform an analysis of variance and test the homogeneity of the mean lives of the four brands of lamps. So we are testing the mean lives of four brands. He has given us those mean lives here of the brand, and in certain cases the observations are missing. We can use it. We have learned that's the merit of CRD. We can do the problem though some of the observations are missing. So these are the treatments. This is the data given to us. So we define your our H0 H1 as there is no significant difference between here the treatments which we were talking about. Here we are talking about the mean lives. There, he says, is there an effect of the treatment on the yield? So here it is the mean lives that we are seeing. We say that whatever brand of bulb lamps you use, the mean lives, there is no change. So there is no significant difference between the mean lives of the four brands of lamps. Like how we wrote, there is no significant difference in the yield of the crop between the four treatments or three treatments which we used in the previous problem. And here, alternate hypothesis, there is a significant difference. So the mean life definitely differs from brand to brand, is what alternate hypothesis is saying. So we shall now check which one of the two is true based on the given data. And the level of significance we are choosing is 5%. So the second step now involves rewriting the data. But as you see here, the data is huge and it deals with large numbers. So, just like how we always say that we can simplify it by changing the scale and the origin. If you look at it, all these could be divided by 10 so that the four digit numbers start becoming three digit. And then we can also choose any one as the assumed mean and then subtract the given value from the origin from the assumed mean value divided by 10, so that all these values will simplify and will help us in taking the squares and dividing by each other values. So we can reduce the complexity of these large numbers. Let's see how in step 2. So as I told you, we are rearranging the given data according to the brands by subtracting from 1650 I have subtracted and I have divided by 10. So the value given to us minus 1650 divided by 10 is what gave me all these mean values for every brand of electric bulb. And once I get this, so the values are definitely simpler than what was given to me in the problem. Then I calculate the total mean life for every brand. Then I square them. I write down the total numbers of sample data that is applied. I calculate mean lives for seven bulbs, then for five bulbs, and then again for eight bulbs and six bulbs. They give me Ri, which is 26, and then I divide Ti square by Ri to get the mean brand value, and so I get G value as the total grand total. N is the total experimental units, which are 26, and I get the mean value as 491.64. Now I move on to computation of squares. So I'm squaring all the Yij. So I square all these values and I add them. I get that value, and minus G square by N. G square is this, and Ng square is 32 square by 26. When I simplify it, I get this as my SST. Moving further, I calculate SSB in a similar fashion. I have this value in my previous table, subtract G square by N, get the SSB value. SSE, by subtracting SST and SSB, I get the value for SSE. I use all these values in my ANOVA table. So source of variation, there it was between treatments. Here I'm writing between brands. K is 4, N is 26. So I check out 22 plus 3 is 25. This is getting satisfied. This is one way of cross check. That's all. R1 is SSB, this value. R2 is SSE, this value. I'm adding up to see I get SST. Perfect. Then I divide R1 by 3, R2 by 22. I get MSB and MSE. Out of this, I find MSB is greater. If you note in my previous problem, MSE was greater. Here MSB is greater, so I write that in the numerator and the smaller in the denominator. Get the calculated value of F as 2.21. So the corresponding degrees of freedom that I need to choose is 3, 22, because the largest is 150, corresponding degrees of freedom is 3. So here I will take 3 along the row and 22 along the column, and I will take this value, which will be 3.05. So 3 along the row, 22 along the column, and 3.05 is the table value. I find that the calculated value is less than the table value, and once again, by my conclusion, the null hypothesis is accepted, meaning there is no significant difference in the mean lives of the 4 brands of lamps. So the procedure is exactly similarly done as in problem 1. We shall do one more problem before winding up this video. So we shall read problem 3 now. In order to determine whether there is significant difference in the durability of 3 makes of computers, samples of size 5 are selected from each make, and the frequency of repair during the first year of purchase is observed. The results are as follows. So we are now asked to analyze the durability of three makes of computers. So 3 makes are given to be A, B, C. And when will we test that? How will we test the durability? It's only if we know that it is the frequency of repair is much less, then we say that particular make of computer has a greater durability. So what did they do? They took the frequency of repair of 5 computers under each brand or each make, and they checked how many times the computer went in for a repair. So and then based on it judge the durability of the make. So there are 3 makes. Earlier we have been writing the treatments or brands along the rows. Here it has been posted along the columns. You could rewrite it in terms of rows and continue the same way as we did problem 1 and problem 2. So now the hypothesis which let's define, the null hypothesis would be there is no significant difference in the durability of 3 makes of computers. Or the alternate hypothesis would be there is significant difference and the level of significance is 5%. Let us rearrange the data in the format we know. In this data, we shall work it out in that direction and then proceed. So the same data given in the table is now rearranged along the rows. The values are all small, so we don't have to subtract them or divide them by any number. So this is the frequency of repair. I've not put commas in between, but you could also put, I just left a gap in between. You could separate them using commas. Then I've calculated TI, that is the total frequency of repair for every brand. Then the square, then the number, how many of them have we given? We have taken a sample of 5, so all are 5s. So totally we have taken 15 experimental units, that is 15 computers. Then we have divided di square by ri to get the summation value. And then we have proceeded by calculating SST. I have squared all these values, yij values, and added them to get 100. 800, and then I've subtracted 666, which is 0.67, which is the correction factor, and that gave me the value of the total sum of squares. So proceeding to the between sum of squares, We have taken the total mean value minus the correction factor to get SSB, then subtracted SST and SSB to get SSE, the error. We have used that in the ANOVA table between makes of computers, error and total. This would be the rows here. Degrees of freedom, we have 3 makes, so 3 minus 1. We have total n to be 15. We have taken 15 computers, so n minus k is 15 minus 3. The total is 15 minus 1. It coincides with 12 plus 2, yes. Then R1 is SSB, R2 is 70. Addition to these two gives me SST. Division of R1 by 2 gives me MSB. Division of R2 by 12 gives me MSE. We find that MSB is greater than MSE. So therefore F value is 31.67 by 5.83, and we find the table value to be this. Now the table value that we take up corresponding to the highest value, the first component is 2, the second one is 12 degrees of freedom. So corresponding to 2 along the row and 12 along the column. Now look at that particular value. This is 3.89 that you find. You can use the same table that I showed you in my previous slides. Now we find that 5.43 is greater than 3.89. So the calculated value is greater than the table value. So according to my understanding, the null hypothesis is rejected. And if null hypothesis is rejected, what is accepted? The alternative hypothesis, that is H1, is accepted, meaning there is significant difference in the durability of 3 makes of computers. So all of them don't give for repair at the same time, but there are certain makes of computers which are more durable than the other two. So this is the kind of conclusion we make from the data that is being given to us. So ANOVA helps us derive this conclusion. I hope the 3 problems are comfortable, and they have given you an insight as to how the design is created and how ANOVA and F-test help us derive a conclusion based on it. With this, we complete this video on completely randomized design. So we started by understanding the features of CRD and then its merits and demerits, and applied the design, understood the design clearly, and then used the ANOVA technique to solve it, and finally derive a conclusion on the hypothesis using the F-test. So the same structure is going to be followed in my next design, which is the randomized block design. And we shall meet again in the next video. Kindly perfect yourself in this particular idea so that this can be extended to two-way classification, which is the other name given to randomized block design. But the procedure that we have followed here is exactly the same. Let's meet in the next video. Hope you all have understood the concept. Goodbye. Take care. We'll meet soon.